Hello, welcome to lesson 14. In this lesson, we are going to look at the astronomical telescope. We have different types of telescopes. We have the reflecting telescopes and then the refracting telescopes. So today we are going to look at the refracting astronomical telescope. A telescope is a device used for viewing distant objects. A telescope in normal adjustment is when the final image of a distant object is focused at infinity. An astronomical telescope consists of two converging lenses. One is an objective of a long focal length and the other is an eyepiece of a short focal length. So this enables a high angular magnification to be obtained. In normal adjustment, the objective forms a real inverted image of a distant object at its focal point, or at its principal focus f0, which is situated exactly at the principal focus of the eyepiece, as we are going to be seeing. So this intermediate image acts as a real object for the eyepiece to give rise to a final virtual image at infinity, as we can see here. So this is the intermediate image, and is formed at the principal focus of the objective, which is also at the principal focus of the eyepiece. Then this intermediate image acts as the real object for the eyepiece, and then the final image is formed at infinity. So when you consider this, let h be the height of the intermediate image formed by this objective at this point Fe, which is also f0. So the magnifying power is going to be given by alpha divided by beta, where when we look at this ray diagram, alpha is going to be alpha is going to be approximately equal to tan alpha, because we are saying alpha and beta are small angles in radians. So it implies that alpha is approximately equal to tan of alpha, which is opposite h of adjacent Fe. And also beta is approximately equal to beta, which is opposite h of adjacent f0. So when you substitute that in the magnifying power formula, we shall have this. If we divide that, we shall get our m, the magnifying power, as f0 over Fe. Now we can note from this that for a high magnification, or for a high angular magnification, or a high magnifying power, f0 must be greater than Fe. So the focal length of the objective must be greater than the focal length of the eyepiece. And also, when we observe this expression, the magnifying power, we need to know that for this formula, the magnifying power is only true for this formula for the magnifying power is only true for a telescope, for an astronomical telescope, which is in normal adjustment. It is only true for an astronomical telescope which is in normal adjustment. When it is not in a normal adjustment, the magnifying power formula will change, as we shall see later on. And the separation between the objective and the eyepiece is going to be given as f0 plus Fe. That's going to be the separation. and the angle beta subtended at the eye by the distant object is practically equal to the angle subtended at the objective, that angle beta, which is subtended at the eye by the distant object, is practically equal to the angle subtended at the objective. So that's why we are using beta, as we are using the beta we are using. We are just getting it from this ray diagram here, because this beta is the angle subtended by the objective, subtended by this distant object onto the objective, which is actually equal to the angle subtended by that distant object onto the eye. So that's why we have used that. Then the other thing we need to note is that from that diagram still, the distance between the lenses is equal to the sum of their focal lengths. As we have seen, f naught plus fe gives you the distance between the lenses. So this provides a simple method for setting up the convex lenses. This provides a simple method for setting up the convex lenses to form an astronomical telescope when their focal lengths are known. So if I know their focal lengths, I just need to set them a distance f naught plus fe apart. Let us also look at the eye ring or the exit pupil and its relation to angular magnification for a telescope in normal adjustment. The eye ring is the best position of the eye when using an optical instrument. At that eye ring, and also need to know that eye ring is actually the image of the objective formed by the eyepiece. It is the image of the object formed by the eyepiece. At that eye ring, or what we call the exit pupil, the eye receives maximum amount of light entering the objective from outside. And so that is usually the field of view. That eye ring is usually the best field of view, or it has the best field of view, or the greatest field of view. So this is what we are talking about. So this objective acts as the object for the eye ring, and then the image of that objective is the exit pupil. This. So if I want to study the eye ring and I want to get this eye ring, consider this as the objective distance, the object distance f naught plus fe, and then this is going to be the lens, and then we shall get its image. So at the exit pupil, the eye forms an image of the objective, as I've said. And so if you consider the action of the eye ring, so of the eyepiece, this is going to be, u is going to be f naught plus fe, and then f for the eye piece is going to be fe. So if I apply the formula 1 over f is equal to 1 over u plus 1 over v, and we substitute this, where u is f naught plus fe, we shall have our v as fe into brackets f naught plus fe divided by f naught. As I've already told you that the objective acts as the object for the eye ring. That's why we consider this to be the object distance f naught plus fe. So the eye ring is going to be at a position of fe into brackets f naught plus fe divided by f naught from this eye piece. Now the diameter of the objective over the diameter of the eye ring is equal to, so if I look at the diameter of the objective, A B, divided by the diameter of the eye ring, which is AB but small. We are going to have that is also going to be equal to U divided by V. That ratio is equivalent to the distance U, which is from here, the objective, up to the eyepiece, over V, which is the distance from the eye ring up to the eyepiece. But we know what U is. U is F0 plus Fe, and then V is this, which we derived, this one here. And so if we divide the two, you can see that we shall get F0 over Fe. So the diameter of the objective over the diameter of the eye ring is equal to F0 over Fe. So if I get that ratio, it's the same as F0 over Fe. So that is very important. But we know that the magnifying power is given by F0 over Fe for the telescope in normal adjustment. So what does that conclude to? It concludes that the magnification, the angular magnification, that is, or the magnifying power, is equal to the diameter of the objective over diameter of the eye ring. So I can get them, if I have the objective and also have the diameter of the eye ring, and I divide the two, I can get the angular magnification or the magnifying power, which is also got by getting the focal length of the objective or the focal length of the eyepiece. So this expression is very important, and we shall have its use. Let us go ahead and look at the refracting astronomical telescope with final image at a near point. So when the final image is at a near point, then the telescope is not in normal adjustment. So this is when, so this is an astronomical telescope. When it is not in normal adjustment, that's when the final image is going to be at a near point. Remember our near point, that is a distance D. Is that distance D from the eye ring, sorry, from the eyepiece. Now, the objective in that case forms a real inverted, in this case, the objective forms a real inverted intermediate image of a distant object at its focal point F0. And that intermediate image is going to be at a distance U from the eye piece, and that means that it's going to be nearer the eyepiece than actually its objective, so rather than its focal length. So we shall look at that ray diagram. But we also need to know that after forming that intermediate image, that intermediate image is going to act as a real object for the eyepiece, which will give rise to a final virtual image between the objective and the intermediate image, and that is going to be at a point which is near what we call the least distance of distinct vision. Let us see what I'm talking about. So we are saying the objective forms an intermediate image at this point, which is going to be F0. This is going to be the principal focus of the objective, and the distance from this point up to this point is going to be U. But we know that this distance from the intermediate image up to the eyepiece is going to be less than the distance from the eyepiece up to its principal focus or its focal point. Then the final image is going to be formed. So this intermediate image acts as a real object for the eyepiece. So this forms an image, then this image acts as the object for the eyepiece, which thus forms an image at a near point. That near point is at a distance D from the eyepiece. So let us try to also derive the angular magnification when it is not in normal adjustment. So we are going to still let h be the height of the intermediate image formed by the objective, at this point F naught. This is going to be a point F naught. So the distance from here up to here is going to be Fe. So the magnification, that is the angular magnification, can still be got using m is equal to alpha divided by beta, where alpha and beta are small angles in radians, such that alpha is approximately equal to tan alpha, which is equal to h over this distance u, and also beta is approximately equal to beta, which is equal to h over the adjacent, which is f naught. This is supposed to be small f naught, the focal length. So when we substitute here and then we divide, we shall get our m as f naught divided by u. F naught divided by u. Now let's consider the action of the eye ring, sorry, of the eyepiece. Let's consider the action of the eyepiece, because we want to substitute for this u. When you consider the action of the eyepiece, this is the lens, so you can apply the lens formula, where v is equal to negative d, because this is a virtual image, and then f is going to be the fe for the eyepiece. So we shall have our u is going to be given as f times v divided by v minus f, and if we substitute for f and v, we shall get it as fe times d divided by d plus fe. That's going to be the u. Then we shall substitute back in our formula that we had derived, that is the magnifying power formula, and when we substitute for u, we shall have our magnifying power, or the angular magnification, as this. And when we simplify, we shall have it as f naught over fe into brackets 1 plus fe divided by d. Let's make a note here. The least distance of distinct vision, that is the d, is the distance from the eye to a point where the eye can see an object in greatest detail. And that distance is about 25 centimeters for a normal adult eye, but less for younger people. So that distance d is usually 25 centimeters for a normal adult. Let's look at the disadvantages of an astronomical telescope. An astronomical telescope forms an inverted final image. That is the disadvantage. Let's make another note. When we observe the structure of the astronomical telescope, we can modify that structure to overcome this disadvantage. You can modify that structure to overcome this disadvantage. And in that case, we shall form an erect image. So that modification now becomes what we call a terrestrial telescope, which we are going to be looking at. We are going to look at that terrestrial telescope in the next lesson. So thank you for your attention. We meet in the next lesson, where we shall look at the terrestrial telescopes. Thank you.